Good afternoon, sim jury. My name is Suleiman Afsinli.
Mustafa Mansour.
Our team presents Project AntaCore. We specialize in developing algorithms for microcontrollers that power rescue robots designed to save lives in environments where humans cannot survive. We begin by analyzing the core issue. During earthquakes and building collapses, rescuers work under immense risk. The bridge is unstable and space is extremely confined. Existing robotic solutions are often ineffective. Why? Because they rely on GPS, preloaded maps, and constant operator communication. Under tons of concrete, GPS fails and silence drops. If a robot loses connection, the mission is over. Navigation in such requires an instant reaction, not static maps. We found the solution in nature. Ants don't have GPS and cannot see the big picture, yet they navigate and see complex mazes perfectly. Our idea is to create a decentralized system, a swarm of robots that function as a single organism, self-organized, with no single point of failure.
And how do we translate biology into technology? Our solution is the AntaCore algorithmic framework. We didn't just get inspired by ants, we performed engineering biology. We took real insect movement strategies and translated them into C++ code. Our algorithm allows robots to balance between straight line movement and sharp search turns. This enables the autonomous network to remain stable even if several units are destroyed. And the novelty of our approach lies in our unique mathematical model, derived through empirical testing. This isn't abstract theory, it is statistical data specifically adapted for microcontrollers operating in confined spaces.
Our first task was researching ant locomotion. We built an experimental arena mimicking real-world conditions using paper, walls, and stones. To ensure natural movement, we utilized synth trails that would allow them to climb walls. We conducted experiments on 100 individuals from a red sheep ant colony from Quebec. We traced their territories using black markings on liquid glass, as shown on the slide. From this data, we constructed a variational series and filled the table, marking the distance intervals covered. The number of ants reflects the absolute frequency. This allowed us to calculate the arithmetic mean. Our mathematical expectation, which was 134.5 centimeters. We applied these results to two probability distributions, Gauss and Pareto, allowing us to analyze the behavior of the majority of the colony. How do we build the normal distribution Gaussian curve? As noted, and then constantly change direction. Our model describes exactly how many ants change direction at each step and predicts their chosen path. The bell curve in figure 4 represents these intervals x-axis against absolute frequencies, y-axis. This curve accounts for nearly 75% of ant behavior. The remaining behavior shows a significant probability of occasional large deviation from the standard path. To describe this more accurately, figure 5 shows the standard deviation, which characterizes the probability of value deviating from the mean. The deviation is 12.85 centimeters. Furthermore, this curve demonstrates the 3 sigma rule, the probability of value deviating from the mean by more than 3 sigma is practically zero. To calculate this, we found the variance representing the spread of data, which equals 165 centimeters. On the slide, figure 6 shows the Pareto curve as a cumulative frequency graph. To build it, we used cumulative frequencies and interval midpoints in the table 3. You can see that the number of ants increases significantly in the 134 centimeters range. This confirms that the majority of individuals deviate from the mathematical expectation within these specific limits, validating our findings from the normal distribution model.
And now let's look at the commercial landscape. The market is shifting. While 2018 era, robots were expensive and lacked mobility. Today's industry demands total autonomy. The market is projected to reach nearly $9 billion by 2028, driven by a private firm, costly individual units to mass-productive, cost-effective swarm system. AntaCore is perfectly positioned to capitalize on this trend. Our potential clients are not only emergency services like the Ministry of Emergency Situations, but also industrial companies for pipe and mine inspections. Our primary value proposition is system survivability, with competitors if the central server fails, the whole operation stops. With our decentralized approach, the loss of one robot does not stop the mission. This is a critical advantage in life or death rescue operations.
To conclude, AntaCore is a project where rigorous mathematics and biology unite for human safety. We are building technology that makes the invisible visible. Here is our robot. We use ESP32. We implemented an algorithm, mathematical model of end dynamic. Here's our robot. Thanks for your attention.
Thanks.